Hi, and welcome to this first training session at Verification Futures. We're focusing on formal, and the title of this talk is What Can Formal Do for Me? My name is Doug Smith, and I'm from an instructor at Doulos. And if you're curious about formal, then this is the right talk for you. So we're going to have a look at a number of ways that you can use formal, and hopefully you can see how you can start to apply it in your current project. To start with, let's make sure everyone understands what formal actually is. I like how the folks at IBM define formal. They say formal verification uses mathematical formal methods to prove or disprove the correctness of a system's design with respect to formal specifications expressed as properties. So what that means is we will write properties about the behavior and intent of our design. And then those properties can be given over to our formal methods, which are mathematical and algorithmic, so that they can explore through the entire state space and try to either prove or disprove that they hold true or not. Unlike simulation, because formal traverses through the design space mathematically, it no longer needs to have a test bench or input stimulus provided because it's going to go through it in its own way. And finding a proof or a counterexample is a really powerful witness of a design's behavior, since formal must traverse through the entire space to actually get to its conclusion. So provided you've written your properties correct, you can actually guarantee that your implementation meets your design requirements. With simulation, we test the design by defining the stimulus and trying to hit all the scenarios. And often we're focused on end-to-end checking to see if everything worked as expected. Instead of comprehensively traversing through the design state space, we settle for representative test cases that follow paths through the design. And provided we've produced good stimulus, we can have confidence that we've done a thorough job of testing. With formal, it works in the opposite way. Formal works backwards from our assertion targets, traversing through a design state space. Instead of defining what stimulus to drive, we tell formal what stimulus to avoid by defining constraints. And so when formal proves a target, we know that all valid combinations have been tested and that our design meets its requirements. Now that we've defined what formal is, let's look at where we can use it. And formal has several sweet spots that we want to focus on. You may think that formal is only used once we have RTL pretty mature, and then we can go in and start verifying things, but actually you can use formal on each of the different stages of your design cycle. We can use it in the architectural planning phase because we can maybe define some sort of high-level model that represents like a cache coherency protocol and then run it through a formal app that can tell us whether there's any deadlock scenarios and so on. Or maybe we want to test that we've defined our microarchitecture correctly. Or another thing that we do with formal is as we write our properties and our assertions, we write them straight from the spec, and formal finds issues, then we go back to the designer and they look at it and say, oh, well, we really didn't define that in the spec. And so formal helps us to kind of firm up our spec so that we can close up any gaps and holes we may have in that as well. We can also use formal as a design checker. So there are formal apps that can automatically extract properties for us, things like missing sensitivity list signals, or maybe you have a module that has always processes that some are synchronous resets, some are asynchronous, and it may cause some sort of timing issue. The formal, maybe you'll find signals that are dead or have maybe X come up in X. And so these things are created automatically for us, and we can just use the formal app to go off and check everything without really doing anything. They're very push button. We can also use formal to explore a design, which I'm going to show you in a slide or two here, so we'll come back to that. And then there are some traditional areas where formal is really good, like clock domain crossing or reset domain crossing, where this is built, these rules are built into the tool, or maybe you have some sort of superlint that has all these rules built in so that you don't have to be an expert on everything. Formal will go off and find issues for us. Then, of course, we use formal for our verification, and this is traditionally what we think of with formal is doing model checking, where you've written properties and you're going to check your model and see if you find any counterexamples and if you can prove things are correct. Of course, we can write those properties. We might actually have some sort of verification IP we get from our vendor that we could use, let's say, on our different bus interfaces. Another area where formal is really useful is for reachability, and we're going to talk about some applications for that. Likewise with equivalence, and we'll come back to equivalence as well. And then we can also include formal into our sign-off criteria, just as we use our different coverage metrics and so on for sign-off from our simulation metrics. We can also use the same type of metrics from formal and include that part of the sign-off. For example, we can see what parts of the design did formal test, how good did it cover the design. We can even use it to measure the quality of our assertions. How are our assertions actually catching problems in the design, and are all parts of the design covered by our checks? And if you have a tool that can do it, you may even be able to generate test plans and use the formal tool to back annotate into that test plan, and you may even be able to use it to generate test cases or to generate coverage exclusions for your simulation run. So we'll look at that in a moment as well. And then even after your chip has taped out and it gets into the field and a customer finds a problem and it comes back to the lab, you may spend days, weeks, even months trying to reproduce an issue that you can't really do because now it's in silicon, you don't have access to things you can't probe. But when things are in silicon like this, if you can capture in the lab what the inputs are and what the different values are that you can constrain your chip, then you can ask formal, show me how to get to this point. And as we said, formal works back from its target. So if you can say, show me how to get to this part of the code, formal can work back and show us how we got into that state. And so this is a really useful and perhaps overlooked application for formal, helping us to go in and debug things in post-silicon. So let's look at a few of these applications. And we'll start with looking at how to explore our design using formal. So suppose you have a simple design here. Here we have a stopwatch FSM. And so we've got two buttons coming in, a reset and a pause or stop. And so we want to be able to visualize this FSM to see what it's going to look like. As a designer, we've written this code. We're most likely going to write a little test bench and write some test cases to actually test this out. However, if we use a formal tool, all we really need to do is to write a simple cover property. With a cover property, we just are telling formal, show me how to reach this match. So we're saying, I want to see the case where the state is equal to the stop. So we want to get to the stopped state in here. Now all I have to do is send this through the formal tool, and then I can visualize it. Our formal tools can create waveforms just like our simulators can. So we have this property saying state equals stop. We ask formal to draw this particular cover property, and so it will come up with a trace, a valid trace, a scenario, showing me how we could actually get into that stop state. The nice thing about this is I didn't have to write a test case. I didn't even have to have a test bench. In fact, even this cover property, while it's written in system Verilog syntax, could have been written as a tickle tool directive. So I wouldn't have even had to compile that. I could have done it all within my script. And so now without having to write a test bench, I'm able to visualize my code and explore my design. An even easier way to generate a waveform is if you use a formal coverage app. With formal coverage, it will run through and analyze your RTL and see if you can reach every line, branch, and transitions and everything in there. So in that case, all you have to do is find the line of code in your coverage app and then say, I want to see an actual waveform. So you select the line and then you say generate a trace. With this, then it will pop up the waveform for me, and I didn't even have to write a single bit of code. Some formal tools even allow you to draw the scenario you would like to see. So for example, here we can select the state in the waveform and that we want to visualize. So here we're saying we want to see the stop state. And then all we have to do is to press this button right here and ask Formal to generate us a waveform that meets that constraint. So as the designer, this allows you to try different scenarios and visualize your RTL to see if it's working as you expected. You can come in here, you can draw it, and it will go off and generate you a valid trace to illustrate what your design is actually doing. Another application, perhaps one of the most popular uses of Formal, is with automatic design checking, since it really is a push button flow. Plus, it can find issues very quickly, and they're often significant issues that you can uncover using one of these applications. Automatic property checking is an example of using a formal app to pick low-hanging fruit. This kind of app uses the structure of the RTL code to infer and generate properties to check for a few common RTL coding errors. Automatic property checking is sometimes combined with linting, but it has the advantage that because we're using these formal engines, not only can we do the static lint checks, but we can also do more complicated dynamic checks like deadlock and live lock scenarios that you would need an actual formal tool to actually cycle your design and clock it through the different state to be able to see if that would happen. Now we could write these checks ourselves by hand, but automatic property checking saves a lot of manual labor. Plus, it can find many types of errors that are not so easy to be detected with simulation. Here's an example. So we have this piece of RTL code, and you can see in this code we're using a vector. We're calling it an array, but really it's a packed array or vector with only 4 elements in it. And we're addressing or indexing into it using this variable called address, which you can see is 8 bits wide. So 2 to the 8 means we have 256 possible values here. And so just by visual inspection, we can see that we're going to be out of bounds when we're trying to access this array. So we run this through our formal automatic property extraction tool, and it generates some property for us like we show here at the bottom. When I have a write, that implies the address should be less than 4. And then we can run it through the formal analysis, and of course it's going to flag this particular line as a failure because it's too large. But what about this one here where we are addressing it by n? Now, the n happens to be defined as an integer. So 2 to the 32 would be like 4 billion values. We would expect that to be out of range. However, n is actually taking the address, which is 8 bits, and we're shifting it to the right 6 times. So in the end, there's only going to be 2 bits of values, which means there's only going to be 4. So we would run this through the formal tool, and it comes back and says, actually, this bound is going to be okay. But what about this last one here? Here we're using k. Again, it is 2 to 32 bits. Now, if the formal tool will honor our constraint that we've written here, we've said that we want k to be greater than or equal to 0 and less than 4, then it should pass. And if it's not honored, then of course the formal tool is going to flag this as an error. So without having to do any sort of manual analysis, we can run this through the formal tool. It'll write the property for us and it'll automatically check and start to flag things that we may need to go back in and look at and ask ourselves, is that really what we intended? Another example of an automatic check is an arithmetic overflow. So here in our piece of code, you can see we're adding this, we're taking the previous value of sum and adding another value to it. And so we would expect that this would continue to add up or count up and reach a point where it's going to hit the max for this size, since this is 4 bits wide. And so we run this through our formal tool. It generates a property that then says the sum plus the address should be less than 16. And this is a case where if our design expects an overflow, then this might be a check we want to waive or we want to turn off. If we do not expect an overflow, then this can flag this as an issue, and then we can go back in and examine it and see, is this something I'm concerned about? Here's another example shown for the unique case. What the formal tool does is generate a couple properties to check whether the case is full case, meaning all the cases are specified, and parallel case, meaning that all the cases are mutually exclusive. So we look here at this first one and we can just visually see that all the cases are being specified. It's also within a unique case statement, so we know that there's no priority here. So that one's going to pass okay. The second one here, we see that we're using variables C1 and C2, but of course we're only using one value of this C1. In other words, we're using the value of 1 for C1 and the value of 1 for C2. We're not using 0 for C1 or 0 for C2. So we haven't fully specified this particular case, and so the formal tool is going to flag that as a potential issue that we need to take a look at. Many automated design checks may be broken out into separate formal apps like your clock domain crossing or reset domain crossing, or even UPF checking. So finding all the clock and reset crossings and implementing all the checks that you would need for that would be really tedious, probably impractical, and it would probably also require a bit of expertise in those subject domains. So this is why formal apps are so helpful to generate those checks for us automatically and then run through the analysis and find issues for us. Of course, the classical use of formal is model checking. So let's have a look at that next. Model checking is where we write our design's behavior in the form of system Verilog assertions and properties, and formal checks that the properties always hold true. And if a counterexample can be found, formal will find it, proving that the design does not meet the expected design requirements. So for example, we might write a property that says we should never see a write enable and an output enable simultaneously, or that the size should be less than or equal to the maximum. Or when we see a write signal come along, capture the value of the size and wait for the ready signal to go high, and then check that the size is actually incremented by 1. Ideally, we want to write our properties directly from the design spec. So for example, here we have a spec that says after a start pulse, stop must go true on the next or second clock and must remain true for exactly 2 clock cycles. And we can describe this behavior below with this simple property that says when I see a start come along, that implies within 1 to 2 cycles later, I should see the stop go high for 2 cycles. And so if we were to look at the things that would be matched by this, you can see these 2 waves would be matched. These 3 waves would not be matched by this property. Another area where formal works well is checking bus interfaces and protocols. So in this example here, we have a simple protocol where we get a handshake of a start signal coming along, and then we get a stop response. But one of the difficulties we have is that we may get multiple start or requests before we get any sort of acknowledge. And so if we were to see a start come along and then wait for the stop signal, we might match the wrong acknowledgement. So what we can do is assign a transaction ID to each of these pulses. And we're going to be able to do that by using some helper code over here that'll keep track of a start and a stop counter so that we can assign a transaction ID to each of these different pulses. Then we'll write a property that uses a local variable in here, and when we see the start come along, we'll grab the current transaction ID for the start. We'll wait between 1 and 4 cycles later until we see the stop, and then we'll compare, did we get the correct stop match here, because we're going to ask, the question is the stop counter equal to whatever we had grabbed for the start counter? So by using this bit of helper code here, we're able to flush out any violations that may exist and be able to perform this kind of almost out of order type of transactional bus protocol. Formal model checking isn't limited to just simple properties. Formal can also perform end-to-end checking, as shown here with a formal scoreboard. Once formal receives a valid expected data as input, it then waits for an actual data to arrive and then compares the two. And the difference here between a formal and a simulation scoreboard is that with formal, we are testing all possible combinations simultaneously, whereas with simulation, we're testing only what the stimulus is driving the DUT to. So this can allow us to actually explore the entire state space, because formal is going to try to find a counterexample of some sort of input that generates an expected data that we don't end up here on the output. There are many applications for formal, but one of the most practical is reachability. So let's have a look at that. With reachability, we're asking formal to find a path through the design to reach a particular target. The easiest form of reachability is using a cover property. In this example, we're asking formal to show us, is there a path to reach the stop state? And if it can find one, then it can generate us a waveform. And so here you can see it's actually generated a trace so that we can see how visually we can get the design to this particular state. Reachability has a lot of applications, like finding deadlock or live lock, or maybe liveness scenarios, or maybe specific applications like security or propagating X. So let's have a closer look at several of these. Something very hard to prove in simulation is liveness. Liveness asks the question, does something, usually something good, eventually happen? So here we have a property that says, when I see A, eventually I want to see B happen. Again, this is something that you really can't tell with simulation, but with formal, if it cannot find a finite length counterexample, then it can prove that something will eventually occur. And so while liveness doesn't prove that nothing bad's going to happen, it will maybe help you verify your design requirements if you have a requirement that says you want to see something eventually occur. Example of something bad happening is X corrupting your design. For example, suppose your design has non-resettable flops and you want to verify that no X's can propagate to your primary outputs. Using a formal XProp app, formal can trace X's through your design and find scenarios where your outputs become corrupted. All we have to do is to either write some properties that'll see whether X can propagate, or if we use an XProp app, it'll automatically create these properties for us. Now you can also do X propagation in simulation, and I recommend that you do, but remember, simulation is only as good as your stimulus. And with formal, the stimulus is being exhaustively explored without any additional setup. So while in simulation you might forget or not be able to drive all the stimulus, with formal, it can check to see if there really is an X being propagated. And if it can find an example, it'll pop up a counterexample or a waveform for us so that we can come in here and see, yes, X really does propagate and reach our primary outputs. Another application for reachability is connectivity. Systems on a chip have a lot of connections, and missing a connection or connecting it wrong can waste a lot of simulation time and debug effort. But with formal connectivity, we can use a spreadsheet of the design's connections and represent which signals are in our design and where they start from and where they're going. We can even specify amounts of delays, because if a signal has to propagate through the network interconnect, then there may be additional delays. And we send this through our formal app, and it will automatically generate the properties for us that we can then run through our formal analysis. Trying to do this in simulation is very tedious, and of course we have to write all the stimulus to do that. Whereas with formal, all we have to do is run it through this app. It automatically generates the properties, it automatically proves it, and it can be done very quickly and efficiently. When we consider reaching parts of the design, security is an important application. Encryption keys stored on a device must have limited access, or else you have a security hole. And since we need to prove that our design maintains security, formal is an ideal choice. We can define where the encryption keys are stored, what modules have access to them, and what valid design paths there are, and formal security app can automatically generate the properties needed to prove that there's proper and limited access to the key storage. So for example, we can prove that the encryption engine only can access this and not something like one of the I/O devices like your USB, or maybe even your microprocessor shouldn't have access to this, or some sort of DMA controller. And so with formal, any possible security holes can be flagged as counterexamples, and then you can go in and fix whatever the issue is. Another form of design reachability is testing the register address mapping and their access modes. Register locations, address mappings, reset values, access modes, and access signals are all provided to our formal app in the form of a spreadsheet and a configuration file, and then formal will generate the properties needed to verify that our registers are doing the right thing, and it'll go off and it can prove or find counterexamples of areas where we have problems with our registers. The applications we've been looking at fall into different classes, and another class that we're going to look at now is formal equivalence. Equivalence checking is verification without test vectors, based on just mathematical comparison of two designs that are intended to be equivalent. It's achieved by transforming the design into an internal representation that the tool can use in much the same way that a synthesis tool creates a gate-level implementation from an RTL description. The transformed designs then are compared to determine whether they represent the same cycle-level behavior. And this technique requires that the designs be synchronous, because in effect it compares the truth tables of the blocks of the combinational logic feeding equivalent registers in the two designs. Areas of the design that are not amenable to equivalence checking, like clock gating or clock multiplier blocks and scan chains, can be excluded from the check by marking them as a black box. What we saw on the previous slide is what we call logic equivalency checking. But unlike logic equivalency checking, which checks if two circuits are combinationally equivalent, sequential equivalency checking checks if two designs which are implemented completely differently still produce the same outputs given the same inputs. Sequential equivalency checking also advances the clock, so it really falls into the category of a dynamic analysis, checking if two outputs are equivalent even if there's an expected clocking delay between the two. A classic example is comparing the implementation between like two hardware description languages such as VHDL and Verilog. When translating to a new language, the functional behavior should still be the same, and trying to develop a test bench and stimulus to test all combinations would probably be pretty difficult in simulation. But with sequential equivalency checking, both designs are compared formally, exhaustively, and without even needing to develop any sort of input stimulus. Using sequential equivalency checking has many practical uses as shown here. So let's take a look at a couple of these applications. One practical example is fault injection. Perhaps you're testing if your design is fault tolerant or if a register can propagate a fault. Using sequential equivalency checking, you can compare a faulted design with the original design. You can tell formal to only compare the output of interest, further reducing its cone of logic to be compared as well. So here we have the original design and comparing it to itself, but we've injected this fault. And then we ask formal, are the outputs still equivalent? If they are, then that means the fault is being masked and the design is fault tolerant. If the outputs are not equivalent, then that tells you that the fault actually does propagate. One of the nice things about sequential equivalency checking is that it can typically handle larger designs than traditional model checking. So that allows us to deal with larger designs and solve harder problems using sequential equivalency checking. A specific example of fault injection is using sequential equivalency checking for functional safety. With functional safety, we need to test if faults can affect the safety path and if the safety mechanism can detect the injected error. And by writing some helper code, we can create a signal for the violation of the safety path and whether or not that injected error has been detected. So we're saying here that if the original output does not equal the faulted output, then we know that the safety path is affected. And we expect that in the original design, the unfaulted design, the safety mechanism will be false, meaning there was no error detected. But we want to see an error detected by our safety mechanism in the faulted design. So next, what we'll do is we'll use a formal directive to cut the net inside of our design to inject the fault. This could be a stuck-at fault, or we could flip a bit, whatever we want that formal directive to do. And then we'll have a cover property that says when we see that particular fault, we're going to call this fault 1. Then we want to see if there's a violation of our safety path and whether the safety mechanism was unable to detect it. And so that allows us then to gather up all these results, and then we can calculate a diagnostic coverage for use in our safety calculations. Sequential equivalency checking comes in different forms. So far, we've looked at comparing RTL to RTL. However, sequential equivalency checking can also compare high-level models like System C, C, or C++ with our design RTL. You might even hear this referred to more as transaction-level equivalency. This is particularly useful with data path verification where the design state space is incredibly large, much too large for simulation or even possibly for formal model checking. So using sequential equivalency checking, which can handle large state spaces due to the design abstractions and collapsing that it does as part of the algorithm, then we can verify models that would otherwise be impossible to exhaustively test. So on this slide, we show a multiplier implemented here in hardware. And using a simple C function that models a 16-bit multiplier, we can use a sequential equivalency checking tool to compare that our C algorithm, or C model, is equivalent to the RTL. And if it's not, then it can flag any issues where things don't match so that we can make sure that our RTL is implemented in the right way. So we've looked at a number of useful applications, exploring the design, automatic checks, the model checking, reachability, and equivalence. Another area where formal plays a significant role is with verification sign-off. When we think of sign-off, we typically think in terms of things like coverage closure, make sure all of our bugs are fixed and all tests are passing. Well, formal can help us with sign-off as well, because with formal, we can use it to generate coverage exclusions for our code coverage. So if there are things that are unreachable that you would never be able to hit, we can go ahead and pull that out of the coverage calculation and therefore get a higher code coverage result. We can even use formal to generate test cases to hit those coverage holes. We can use formal to tell us what the quality of our assertions are, to tell us if we're really covering all the RTL, have we checked everything? And then formal itself has coverage. We have a form of code coverage. We refer to it as a cone of influence or a proof core coverage. And then we can also use formal to do things like generate test plans and test cases, and then use it to back annotate into those plans. And then again, with reachability, that can tell us if something is not reachable, if there's dead code, so that we can again pull that out of our targets, our coverage that we're trying to hit, so that we don't waste our time on things that don't matter. One way formal complements simulation is in generating coverage exclusions. Since formal can prove if a statement, branch, expression, or transition is reachable, it can automatically generate code coverage exclusions for simulation for those elements that are unreachable. In fact, formal tools can read in simulation databases so that they only analyze the things that have not already been touched. Unreachable elements in the RTL make it difficult to reach 100% code coverage, so using something like a formal coverage app to generate the exclusion is really helpful, because it's a push button flow that can remove the extra effort needed for reviewing and filtering out these unreachable parts of your RTL by hand. And even if your formal tool doesn't automatically work with your simulator, you can typically script it out to generate whatever format you want. Here's an example of one formal tool that you simply say generate the exclusions, and then inside of the exclude file, you'll see it'll create different tickle commands for your simulator to say, I want to exclude this particular line in this particular file, and then that helps you to filter that out of your coverage. Some formal tools have the additional capability to automatically generate test cases to hit holes in your simulation coverage. So formal analyzes the coverage database and then figures out a way to target anything that's not covered. And then all you have to do in this particular formal tool is say generate test cases, and it'll create a module with an initial block in here to actually force the design into the state in order to hit that coverage hole. You can include these modules, these test cases, as part of your regular regression flow. You can also make this work with a UVM test bench by setting your agents to passively monitor while the generated test cases drive your stimulus. Another thing formal can help us with is measuring the quality of our verification checks or assertions using a thing called mutation coverage. The idea with mutation coverage is that the formal tool will automatically inject faults into the RTL, represented here by bugs that we've injected, and then measure which of those faults are detectable by your assertions. And this will tell us the quality of our checks. You know, typically we focus on 100% code coverage, 100% functional coverage, but that only tells us about our stimulus. It doesn't tell us if we've really checked all the parts of our design. And if we don't check our design, then we haven't verified our design. So with mutation coverage, what it can do is it'll actually tell us whether our assertions are picking up these bugs. So for example, if there's a bug inside of our RTL that lies outside of the cone of influence of any of our assertions, then of course that's an undetected type of fault, and that tells us that we need to go back, look at our assertions, and ask the question, why is this not being picked up? Maybe we need to add some more assertions to cover all the different parts of the RTL. If we have a fault that's in the cone of influence and it's being detected, in other words, the assertion fails, so we've caught it, then that's a good thing. That tells us that that particular assertion is doing its job. What we don't want to happen is to have a fault in the cone of influence that goes undetected, because that tells us that our assertion is not written well enough. So again, we need to go back, look at our asserts, and figure out how can we make this better. So formal complements our simulation coverage. It fills in both code and functional coverage holes. Just as we include simulation and emulation as part of our sign-off criteria, we can also include formal in our verification planning and define similar sign-off criteria using formal as well. So we can look at the assertion density. Do we have enough assertions? We can look at the code coverage and functional coverage just like simulation. And then with mutation coverage, we can really measure the quality of our test bench, of our assertions, and see whether we're really checking and verifying everything. Lastly, formal is particularly useful for another application, and that is post-silicon debug. Finding problems in silicon in the lab or what gets reported back from the field can be particularly difficult to root cause analyze. Using formal, you can capture as much of the input setup as possible, and we can describe that in terms of our constraints and our assumptions here. And then we can ask formal to hit the scenario that we're interested in. Here we're saying we want to find a path to get the state machine into the error state. Now, if you were trying to do this in a lab context where you have a piece of silicon and you have no probes to be able to get into that, it's going to be difficult to recreate that scenario. But with formal, we can just ask it to show us a waveform of our cover property, show us how to get there, and remember that formal works back from the target, so it can generate that waveform so that we can then visualize and see how did we get into this error state. So while it's not necessarily an easy process to set up, post-silicon debug with formal is much easier than trying to debug blindly in the lab with a piece of silicon that has no probes, or even if you have some sort of debugging capability, it's still easier to be able to do this with formal and bring up a waveform. So let's wrap up what we've talked about. So formal complements simulation and helps you to automate parts of the verification flow that's hard or tedious to do in simulation, like when we talked about looking at connectivity and register checks and that sort of thing. We can also merge formal coverage with simulation coverage, and we can use formal to help us to even fill out our simulation coverage. Even if you don't want to do formal model checking, the nice thing is that there are automated design checks that you can take advantage of. Many people call that superlint. And then there's other push button apps that we can use to verify our design and get low-hanging fruit out of it. And it's really something very simple that can be incorporated to any verification type of flow. And if you're not currently using formal, I'm sure there's a place where you could use it and it would help you out in your current project. With that, I hope you found this information helpful. And if you'd like to learn more about formal, Dualos is a training company. We do have a class on essential formal verification, as well as we offer training in system Verilog and system Verilog assertions. So that's all for now, and thanks for joining us today.